let's move on here into today's topic. So centroids of areas by integration. And actually I've got some pictures here from an Italian cruise ship. Oh my gosh, wouldn't it be nice when we can take cruises again? Has anybody ever been on a cruise? I went on my first cruise like in 2019. It was super fun. But anyways, so this Italian cruise ship sailed too close to the shore, and it got partially submerged. It basically crashed. And I guess it was this it was this Italian captain that was showboating and like driving really close to the shore or something like that. So they actually were able to salvage the ship. And the way they were able to do it was they actually used the center of gravity. They changed the center of gravity of the ship in order to salvage the ship. And so they had these caissons. So right up here they had these caissons, and they would fill those either with water or with air. And so these are just these big steel tanks. That's where the caissons are, these big steel tanks. And they fill them with water or air to change where the center of gravity is. And then the other thing that they did is they basically created a moment, this tendency to rotate. They have a force that's going here, and then they had a pulling cables down here like this. And they were worried about this thing just continuing on and rolling down into the bottom of the ocean here. And so then they put the caissons on there, and they emptied those caissons there. And then the other reason they used the caissons and they could fill them with air was so that for the buoyancy, right? So that the ship, once they righted the ship, it didn't just sink back down to the bottom again, because they weren't sure what the buoyancy was going to be of a damaged ship. To give you an idea of the relative size of these things, here's those caissons right here, these big white tanks right there. Look at the chains that are attached to it, and relative to the person that's standing right here. This is a person that's standing right there. So each one of those links is almost the same size as that person. So we're talking about some huge, huge forces on this thing. But a lot of statics concepts, in particular then related to our centroids, is explain when the center of mass is equal to the center of area. And so does anybody know, when is the center of mass equal to the center of area? And I have my little balancing bird here that I brought in. And so if I kind of have this thing kind of spin around in my hand, you can see it's balancing on the beak right there. But anybody, when is the center of mass equal to the center of area? Like, is my balancing bird if you look at the area of this thing, it's right here, and I'm balancing it right there on its beak right there. So when is the center of mass equal to the center of area? Yeah, Aiden, thank you. When we have a uniform density. Absolutely, right? This one does not have a uniform density. Excuse me. Does not have a uniform density. Actually, all the weight on this one is in the wings out here, and so that's why it can balance right there on that beak, even though it seems like the center of area is probably maybe somewhere back here, but it's not going to balance on that back there. So yeah, so everything in statics, we're going to assume that it's a homogeneous material. So the other way to say uniform density is to say it's a homogeneous material, which means it has the same density throughout. Our other learning objectives are to draw a picture. So pictures, these problems that we're doing today are very much calculus type problems. And so that picture is super important of a two-dimensional differential element for dx and dy, and labeling all the associated dimensions and distances will just make our lives super easy, and it'll be nice and easy for us to do these problems. And then once we can draw that picture, then we can calculate the centroid of the shape bounded by one or more linear or nonlinear functions. Okay, so we're going to see problems like this. This isn't a homework problem, but we've got a linear function here on top. We've got a nonlinear function here on the bottom, and we'll come back to this. But I'm showing this picture because this is all the dimensions that we need to be able to draw all this stuff in here. And so right now we're looking at that and just being like, oh my gosh, we got to be able to draw all that stuff. Well, I think it'll become pretty straightforward by the end of today's lecture. For homework, the first homework problem in this topic, we're asked to find x bar and y bar. When we see the x bars and the y bars, that means the centroid with respect to the x-axis. So that would be like our x bar and y bar in this problem. If we think about where would that balance, like where would we have to put our finger for that area to balance? Wouldn't it be about like maybe right here? So we put our finger about right there in the, and I'm just kind of guessing, right? That would be the centroid of that area, which would be the center of mass as long as this is homogeneous. And then in the y direction, maybe it would be about right here. Maybe about right there. And so that point, that's what our x bar and y bar is. That's what we mean when we say x bar and y bar. We need to find the centroid. In this problem, another nonlinear function, we're asked to find y bar. And then in this problem, another nonlinear function, we're asked to find x bar. Now this is not due until after the exam. Okay, this homework is not due until after the exam. So take good notes so that when you get to this homework, it's nice and easy. You have nice, good notes to refer back to for the for that homework. Okay, so I'm going to go up here to where we started this review for our equivalent systems, because what we're going to do is very much related to this. And actually, let's just jump right into an example for our centroids by integration. So we can put a new title on here. This is our centroids by integration now. And I guess this is kind of a shortened title. The full title is centroids of areas by integration. And so if we have a shape here, and let's look at a shape that's similar to the homework problem. So let's say we've got a y-axis here, and we're in 2D again. We got an x-axis here, and let's say we've got a shape that looks something like this, and it is a y equal to x squared. So just a nice, easy, nonlinear function for us to deal with here, and we can bound this from 0 to 4. So we're going to go say, well, we want to do 0 to 4 meters here. So this is going to be 4 meters right there. And so they want us to find, for this problem, what they're asking us to find is x bar and y bar. Which x bar and y bar, that would be the centroid of the area. Maybe it's about right there, just kind of guessing. So x bar and y bar. What we're talking about is the x distance, right? So that would be that distance right there. That's our x bar. And this distance right there, that would be our y bar. So find x bar and y bar. I think we're done, right? We just kind of say, hey, we found it. It's right there. And we can just, that's all we have to do. Has anybody seen that? There's a cartoon about that, right? It's like find x bar and on a test, right? And the person just circles it and says, it's right there. There it is. And actually, so right, we're not just trying to find it. We want to find the values, right, of x bar and of y bar. And so actually for our solution, we're going to take, the first thing I want to do is I want to look at a simplified approach, okay? And this is really just to demonstrate the concepts. We're not going to do this on the actual homework, but it's going to make the homework, I think, a lot easier if we look at this simplified approach here. And so let's draw, and then we'll get into the actual approach. We'll use the same problem. We'll get into the actual approach here. So let's say we have our shape here, x and y, and it's, looks something like this. And the other reason I like to do simplified approaches is because like lots of engineers like to do simplified approaches, right? If we can make the math easier for us, if we can like make the problem easier and it's still a good approximation, then that can be super valuable. But this isn't why we're doing that. We're just doing that so that we can look at these concepts. And so what I'm going to do is, I have this nonlinear function here, right? Y is equal to x squared. Well, let me break this down, and I just want to I'm going to make two rectangles to approximate. Instead of having y is equal to x squared, what if I just divided this like right in half, and I said, okay, well, this is a distance here of 2 meters, and then I've got another 2 meters that's right there. And maybe, let's see, I can move that over so it looks like it's a little bit more like right in the middle. Okay, so now I'm going to take and I'm going to make a rectangle that's right there in the middle, but I'm going to make my approximation pretty good. And so what I want to do is I want to actually make this rectangle so that I intersect the function in a way where I'm over approximating and under approximating. In calculus, this is what we would call a central difference method, right? We're like right in the middle. And so we have like this area up here is under approximating, this area over here is under approximating. And so then my next rectangle, I'm going to do the same thing. So I'm going to under approximate and over approximate. And so now we've got these two rectangles here. And I think if we know what the function is, can we figure out like what the height of each rectangle is? We know what the base of each rectangle is, but we can figure out the height of each rectangle. And then can't we find the area of each rectangle? And also, wouldn't we know where the centroid of each of those rectangles is located? Because for a rectangle, where is the centroid? It's just halfway from top to bottom and halfway from left to right. And so these are the same things that we need to be able to label when we get into the actual approach that we're going to use. But like, what would that height be right there? Or like, what we need to find this height right there. Well, the key is that we know what is going on where we intersect right there, right? Isn't that, what's the x coordinate at that spot? And let me call on here Chloe. Chloe, what's our x value at that spot right there? I can barely hear you. I don't know if it's just me. Let me turn up my volume. Go ahead again.
Would it be around 3?
Yeah, it's it's around 3. It's exactly 3. I'm assuming my picture may not be perfect. And so I'm just assuming, yeah, we're right in the middle though. 3. And then doesn't that mean that we can find the y value? Because that would just be x squared, right? So if we know what x is, we can find y, because that's just a 3 squared. And then we can do the same thing over here. And so that's going to have an x value of 1, and that's going to have a y value of 1 as well, isn't it? Which then means that we can find the height of this. The height of this is 9. The height of this one over here is just 1. Okay, that's really key. That's like our first thing here, is that we just need to be able to find the dimensions of our rectangle. The rest of this is going to fall into place. The centroid of each rectangle is going to be halfway from left to right and halfway from the top to the bottom. We're going to call the centroid of each segment of each rectangle x tilde and a y tilde. I'm going to call that x tilde. I'm going to call that area on the right, I'm going to call that area 2. So it's going to be x tilde 2, y tilde 2. And then this one right here will have a x tilde 1 and a y tilde 1. Now, we can use the same concept that we did for equivalent systems to find x bar. Wouldn't x bar just be the same idea as this weighted average? And so wouldn't it be, instead of in terms of F's and D's, how about area 1 times x tilde 1 plus area 2 times x tilde 2 divided by A1 plus A2. Or then y bar would be equal to A1 times y tilde 1 plus A2 times y tilde 2 divided by A1 plus A2. And if let me go back here and grab, right, what did we do with the forces? We did exactly the same thing, didn't we? We just have, instead of an A1, we have an F1. Instead of a D1, we have a Y tilde 1 or an X tilde 1. And so it's exactly the same approach as we did with the equivalent systems stuff. Okay, so let's plug in our values here. So A1 would just be equal to a 1 times the 2 meters, right? Which would be 2 square meters. We know that A2 would be equal to 2 meters times 9 meters, which would be 18 square meters. We can find X tilde 1. X tilde 1 is going to be equal to what, Chris Comey? What would X tilde?
Me?
Yes.
Oh, Como?
Como. Okay, sorry.
I don't quite know.
So what we're talking about, and this is why I stop and ask those questions, because I'm sure if you're not getting it, and other people, but that's our, right? It's just that distance right there. It's just a coordinate. What is the coordinate at the centroid of that area 1 relative to the X and Y axes?
Wouldn't it be like 0.51 or 1.5?
Not what, it's 2 meters from here to here.
Yeah, so wouldn't it be in the center? That would be 1 in the X direction and then 0.5. Oh, I'd just do 1.
Yeah. So in the right. So in the X direction, it would be 1.0, and then meters.
And the Y, it would be 0.5.
Yeah, let's just do, thank you for both of those answers now. So Y would be 0.5. So now we have X tilde 1, we have Y tilde 1. And then X tilde 2 would be the distance all the way out to the centroid of area 2. So we're trying to get what's the X coordinate of that. Isn't that 3 meters? And then Y tilde for segment 2 would be half of the height, which would be 4.5 meters. Okay, so now we have everything. We could plug these into our weighted average. Just for completeness here, X bar would be equal to 2.8 meters. And we would find Y bar would be equal to 4.1 meters. And, you know, just so we're like, just for kind of a gut check here, do those numbers make sense? Let's look at the X bar. You know, we know our 2 centroids are at 3 meters and at 1 meter, right? We have, here's our 2 centroids. We know that segment 2 is definitely bigger. And what do we see? The weighted average, the X of 2.8 is definitely closer to 3. So that makes sense, doesn't it? And then how about 4.1? Well, 4.1 is definitely closer to 4.5. That's the bigger area. So again, it makes sense with what we talked about in today's quiz on equivalent systems and also from last time on equivalent systems as well. Now, let's say we go into, what if we do, instead of just 2 rectangles, what if we did like 5 rectangles or, you know, 10 rectangles or something like that, many rectangles? Couldn't we say like, well, this would be, we could do like X bar would be equal to the sum on X tilde A divided by the sum on A. And right, we could do, so we could do, you know, maybe 5 rectangles or 10 rectangles with that, and we would get more accurate. Now, what about if we went to infinite rectangles? Then what concept are we introducing now? We're introducing infinite rectangles. Wouldn't that be X bar would be now using what? What mathematical operator are we going to do now? Integral, right? Yeah, I was right. We're going to do the integral. So X bar. So instead of having the sum, it's just the integral. We still are going to have an X tilde. And instead of an a, we're now going to have a differential element a. And then we're just going to integrate divided by the total area, which is just dA. And then y bar would be equal to the integral of y tilde dA divided by the integral of dA. So this is what we are going to use, okay? So we'll use these from now on. We don't need to do the approximation or anything like that, but let's look at now if we have our area here. So same problem. We still have this. Y is equal to x squared. And we're still going to go from 0 to 4. Like that. And we're still looking for x bar and y bar, but now we're going to do this with an integration. The advantage of us seeing this with the two rectangles is that now we're just going to do this with a representative rectangle, a representative differential element. And the representative differential element, when we integrate, what happens? The integration just basically just makes those rectangles infinitesimally small, doesn't it? Right? And actually, when you mash the integration button on your calculator, it doesn't do it analytically. It does it numerically. Like if you found the area of this function right here on your graphing calculator, it just breaks it up into about 100 different rectangles. And it does everything that we just did with those two rectangles, but for the 100 of those. And so let's draw that representative differential element here and label those same things. Like we know that, and I'm doing a dx. We'll do a dy here in a second. For that dx differential element, we know that the dimension along the base of this here, that is just, I kind of squeeze my 4 meters in there. Let me move that down a little bit. So we know that distance right there, that's our dx distance, right? It's just that we're doing a dx differential element. Again, just like we did before, the key point, right, in order for us to figure out our height of those two rectangles that we started with, in order for us to figure out then the centroid, we have to know where we cross that function. Now, if this is representative, that's just now some x and y. But if I know what x is, I can find y, right? And so we're just doing the same thing, but we're just doing this symbolically. And so then the height of this, so the height of that rectangle, we're just going to call y. We know, so now we can find our areas of that differential element. Can't we find, at this point now we can say, well, dA, isn't dA just a y times a dx? It's just the area, it's just the width times the height. Is all we're doing for dA. Now, how about for x tilde and for y tilde? Well, we know that's going to occur at the centroid of that rectangle. So there's our x tilde, y tilde. And because we're doing a central difference, doesn't that mean that x tilde is exactly the same as x? And then y tilde, which would be that distance there, y tilde is y over 2. Just half of y, isn't it? So x tilde is equal to x, and y tilde is equal to y over 2. Now, I haven't done any substituting yet, right? I'm just leaving everything. We are doing a dx, so we can't have a y in there, but I'm going to do my substituting later. So let's do it here. So we can find x bar now. X bar would be the integral, and we are going to, this is a definite integral, so from 0 to 4, because we're doing a dx differential element. And then we have times an x tilde, which is just x. So x tilde times dA, and then divided by the integral of dA from 0 to 4. And so this is going to be the integral from 0 to 4. X tilde is just x. dA is y times dx. And then divided by the integral of 0 to 4 of y times dx. And so if we start doing some substituting now, we can, we'll take a, well, actually I see a question in the chat there. So y tilde is equal to 1/2 y because we know the total height is y. The total height of our rectangle is y. So that means the centroid of that rectangle has to be is exactly half. Just like we did on these ones over here with the 2 rectangles, right? We know this distance right there is going to be half of that 9 because it's halfway from top to bottom. Okay, and awesome. Thank you. Great question. Okay, so x bar then. I need to substitute, right? We know, let's throw this in here. We know that y is, we're going to substitute that out. That's going to be an x squared. That one we have to substitute out, right? Because we're doing dx, we can't have a y floating around in there. And so we'll take the integral from 0 to 4, x times x squared dx divided by integral from 0 to 4 of x squared dx. If you want to, for statics, if you want to mash this in your calculator, if you want to do this by hand, either one of those is going to work for us. We're not really, we're not going to test your ability to solve crazy integrals. We're going to test your ability to set up the integrals, and so we're not going to give you any crazy integrals on an exam or anything like that. They should all be stuff that you could do analytically so that people with a graphing calculator aren't advantaged over people that don't have a graphing calculator. So when we plug this in, we're going to find 3.0 meters. Again, this still makes sense in terms of what we looked at before. Also, this isn't why I did the approximation of 2 rectangles to begin with, but look at how close we are to the 2.8, right? This is an analytic integral, so it means infinite number of rectangles. We got we got super close to the 2.8 with just 2 rectangles. But again, that's not why I did it, but just kind of cool to point that out. Okay, and then y bar, we can do the same thing here. Y bar, we know is the integral y tilde dA divided by the integral of dA. And so we can still use a dx, differential element. All right, I'm going to use a dx for both these, and then actually next we'll do a dy for the same problem. We'll at least draw the picture. So let's see, we know what y tilde is, so we go y bar is the integral of y tilde, which is y over 2. dA is y times a dx. We're going to integrate from 0 to 4, and then we have the integral of y times dx. So the base is, or not the base, but the denominator is the same as before, right? Now again, though, we have to substitute out all of our y's, where those are all going to be x squared. That's going to be an x squared. And so we're going to find that y bar integral from 0 to 4 x squared over 2 times an x squared dx divided by the integral 0 to 4 x squared dx. When we plug that in, we're going to find that y bar is equal to 4.80 meters. So not as close as our approximation with 2 rectangles that we did before, but again, that's not why I did those 2 rectangles. It's just so we can really see what we're drawing, what we're trying to dimension when it's a representative differential element. Because it's the same idea, right? Whether it's just drawing one rectangle that the integration is going to basically make, a bunch of, or whether it's drawing just the 2 big rectangles, it's the same things that we're having to label. Any questions? Okay, we can use either a dx or a dy on any of these problems. Let's look at if we did the same problem using dy. So same problem still. So we've got our y-axis, our x-axis over here, our function. look something like that, still bounded from 0 to 4 meters. And now let's do a dy. So a dy would look something like this, right? And so this is what we have to draw, right? This is what I'm telling the learning objectives say to draw this. There's our dy differential element. So we know the height of this now is a dy. What is the width of that now, though? Mandolin, any, like, what's the equation? What would we, like, give me, like, the most, like, basic equation for it, or idea, whatever you want to do. There's Mandolin here. Okay, and I actually see, we'll just move on here. Yeah, Kalev got it. He said 4 minus x. Absolutely right, because now watch out for that. This distance here, that is x, isn't it? And so that distance is 4 minus x. So again, that's why it's so important that we draw these pictures, even though you might think, oh, it's just, it's really easy. Just draw the picture, to spend the time drawing the picture to get that on there. So now we know that dA is equal to 4 minus x times dy. Just width times the height. And of course, we have to get rid of the dx now, or not the dx, we have to get rid of the x because we're doing a dy. And so our function is still, I didn't write it up here, but our function is still y is equal to x squared. And so x we know then would be equal to the square root of y, isn't it? Okay, so we're definitely gonna have to substitute that out there, but we have our dA. And then the other thing that we're gonna need is the x tilde y tilde. So halfway from top to bottom, that's our x tilde and our y tilde. So there's x tilde and that's our y tilde. X tilde is the distance. Remember, it's the distance all the way out to that spot right there. That's distance right there is x tilde. This distance to there is y tilde. So y tilde is pretty easy. Y tilde is just y. X tilde, though, is a little bit harder, isn't it? What if I told you, let's put some numbers to this. What if I said, you know what, this value right here for our particular differential element, let me just throw some numbers. What if this was 3 and, well, and we know this over here is 4. What would x tilde be, anyone, if the left end of that rectangle is at 3 and the right end is at 4? What's the numeric value? Anybody? 3.5. Right? So how did you, that was easy, wasn't it? Right? Because isn't it just like right, as you know, it's right in between. Okay, so if that's 3 and that's 4, now what equation is that coming from? Conceptually, it's, you know, it's just right in the middle. The equation, though, is that x tilde is really the average of the left and right of the rectangle. And so what's the left? Isn't the left x? And the right is 4. So it's really just, let me write it over here. So isn't it x plus 4 divided by 2? Or the way that Kalev wrote it is also correct, right? Because you have 4 minus x over 2 plus x. Because you take half of that plus you add what's to get to the left side of that rectangle. But we can always use the average, right? And isn't the equation for an average, you take, like, you know, if we plugged in our 3, so 3 plus 4 divided by 2 is 3.5, isn't it? So we can always use the average there. So x tilde is the average of those two. And then, so now we have everything, right? We know, like, let's see, we wrote dA. Let me just write, x tilde is equal to x plus 4 over 2. Y tilde is just equal to y. We would have to substitute out x, the square root of y right there. And then we could plug it in. And so, like, for example, x bar would be the integral from 0 to 16, because we're going to x squared, right? So as we're integrating the 16, that's a 4 squared, because we know the x value is 4. And then, so let's see, it would be an x tilde times a dA divided by the integral of dA. So I'm gonna stop right there, because we found everything that we need to plug into our equations. Well, let me go ahead. I'll do y bar 0 to 16. Well, the bottom is 0 to 16 also. 0 to 16 y tilde dA divided by the integral 0 to 16 of dA. And we have all that stuff to plug in. But actually what I want to talk about is, in this problem, which one is easier for this one? Was it dx or dy? I think dx would be a lot easier to integrate, wouldn't it? Because we don't have, I think dx, because we don't have the square root of y, right? Square root of y is harder to deal with. And also because of the 4 minus x thing, right? We had to do that whole 4 minus x thing. So think about those, when you're trying to pick, like, oh, should I do a dx or should I do a dy? Think about, oh, should I, what am I gonna have to integrate? Would I rather integrate x squared, or would I rather integrate the square root of y? And then also think about, well, which one of those is going to be an easier area to determine? Which one's going to have an easier dA? Is it going to be dx, or is it going to be a dy? So we can look for, easier functions to integrate. Easier functions for the integration. And for the, maybe more simple dA. Okay, so what about, I showed you that very first problem I showed you with all those dimensions on there. Let's take a look at that problem, and let's see if we can decide if we can draw all the dimensions, and if we can figure out all of our inputs that would go into our x bar and y bar equation. So for this one, we had a linear function here, and this linear function is, we'll call it y1 is just equal to x. And then they had this nonlinear function too. And let me draw this. Let me draw this a little bit flatter here. There we go. Okay, so the y is equal to x should be at a 45-degree angle, right? Okay, and then we've got a nonlinear function here. And so that's y2 is equal to x cubed over 9. So first thing, dx or dy? What does everybody think? Or are people already answering? Is that what Alex and okay, dx, right? Yeah, I'd rather do a dx because dy is going to have the cubed root in it, and I don't want to deal with that. Okay, so we're going to do a dx differential element. Absolutely, I'm going to draw it. One thing about these differential elements is it really helps to draw them bigger. And I think that's not just because I'm old. I'm not old. I'm just older than most of you. I just think, it's just nice to actually be able to see what you're labeling on there. Okay, so now we need to figure out the width of this and the height. So, right, wasn't that our first thing? Is like, let's figure out the area. We just need to find dA. So, well, we know the width is dx. What about the height of that? What's that going to be equal to? Isla, Carignan. What do you think for the height here? What would that be? Okay, not Isla. How about Ivan Chavez? Okay, no Ivan either. Anyone? Oh, there we go. Luke got it. Y1 minus Y2. Absolutely right, because Y1 minus Y2, because we know this up here, that's where we have some X and Y1, right? And then this one down here, same X, but it's Y2. So Y2 would be this distance to there, and then Y1 would be the distance all the way up to the top of that thing, isn't it? Okay, so now we can plug in our dA. dA would just be Y1 minus Y2 times dx. Now we got to do our substitution, but I like to do the substitution after I've done all the dimensions. I don't have to worry about two things at once. Now, how about our centroid of this thing? So there's our centroid right there. That's our x tilde, y tilde. What would x tilde? Isn't x tilde just all three of those points right in a line right there? So x tilde is just equal to x. And then y tilde, how did we say we did that before? With the, right, when we have a rectangle, this one again, if I told you the bottom was at 3 and the top was at 4 meters, for example, then wouldn't that be 3.5? So the average between the two is a y1 plus a y2 divided by 2. Now, be careful there, because there are instances where we do need to know like half of that distance, right? Half of that height. That would be y1 minus y2 over 2. But we want all the way from the x-axis there. That's our y tilde, is that, which is going to be the average between those two. Okay, so all we need to do is plug in our y1 and y2 with the x equations, and we can plug it into our weighted average integral equation. I guess I didn't even provide the bounds on this one, but we would, whatever the bounds are on this one, we have to incorporate that as well. But if we look back at that picture that I first showed you, we would see this is all the stuff that they had labeled in there. So it looked like a crazy picture, right? But actually, isn't it just finding the area of a rectangle and where the centroid of the area of a rectangle is? And then plugging that into our weighted average equation. You all have a great rest of your Wednesday.